The subject today is integrate well and pre-stack data for lithology prediction. The outline of the presentation will be the following. First, an introduction where we will review the challenges, where we will understand the foundation of the method that we are proposing. We will after that go through an introduction to the methodology and more specifically what is the Democratic Neural Network Association. We will review its application on the case study, a carbonate reef stating, and we will go through a conclusion. When talking about facies distribution inside the reservoir, which is the main challenges that is facing the oil and gas industry trying to characterize a reservoir, we understand perfectly that successful hydrocarbon exploration and production requires the prediction of lithofacious distribution throughout the reservoir with precision. Reservoir facies determination is one of the uncertainties in reservoir modeling studies. It is important since it will affect the reservoir property distribution. And of course, inappropriate determination of the facies distribution may give unrealistic reservoir behavior. So, to conclude this, we need to be able to capture the lateral and vertical heterogeneities regarding the facies distribution, and we need to make sure that our models take into account the facies distribution away from the wells. When we talk about seismic facies, we talk about using seismic data. We talk about unsupervised or supervised processes. You have one example on the right at the top, which is a waveform classification in the Eagle Ford, and you can see, for example, the neurons here at the tops, which is the synthetic model that we have applied to the seismic data, and you can see the distribution or variation in the facies classification. This process was unsupervised. For that we have used the waveform, and we have used the most common algorithm applied in such technology, which is the neural network technology developed by Cohen in 1982, which is a self-organizing mapping approach. We can use several different approach using a multi-attribute approach. So we will, you can see at the bottom, this is the Eagle Ford. This is a seismic facies volume, for example, where we were able to detect from this interpretation, okay, the sweet spot, the extension of the sweet spot from the different seismic attributes. So here we are using a multi-attribute approach. It's a quantitative approach. Each bin size will be associated to a specific facies, and it will use some algorithm like partitional or hierarchical clustering. But in fact, what are the facts that we are facing here when we do such a workflow, we apply for such a workflow? First of all, we talk about post-stack domain, we talk about seismic data, and we need to recognize that the data have already a certain organization. The post-stack data seismic classification, when we use some clustering techniques like the neural network technology, is mostly based on data density. We try to recover what is the most common seismic response wavelet pattern in the seismic data. Eventually, it could be based on data characteristic if we take into account a multi-attribute approach based on the selection of the seismic attributes that will be more focused on data characteristics. And of course, we need to take into account a nonlinear relation between what we observe at the well location, the well facies, and seismic attributes. And this nonlinear relation, it's mainly because it will depend on the geological context and its variation laterally, the seismic quality, and the availability of the seismic attributes. And to close this discussion, we have data from different origins and resolutions. logs, core, pre, and post-stack data. So what is the foundation of the method that we would like to introduce in this presentation? The main goal is to combine geological, lithology, and geophysical data, but we would like to use a rich seismic data set. So we will take into account the pre-stack information and no more post-stack attributes. We would like to apply for a methodology to infer qualitative information such as lithology and facies interpreted at wells from the 3D attributes, seismic attributes. So we want to find patterns in the seismic attributes for predicting what we observe at the well using a probabilistic lithology type approach, distribution, and uncertainty. So we want to create an operator. We want to create this operator using learning techniques, and it could be defined as follows, as a function of lithofacious distribution. Lithofacious distribution will be defined as a vector of lithofacious distribution around one point of interest. G is the unknown operator that will be evaluated during the learning stage. S is the seismic response vector obtained from seismic attributes, such as, in our case, pre-stack angle gathers. So now we will introduce to the methodology that we would like to propose, which is the democratic associative neural networks. The first point, and very important, is that it's a supervised learning approach. So we will learn from the data from which input variables and theoretical response are known. We want to establish a relationship between input seismic data and its corresponding lithofacious index defined using a set of neuron vectors using a given algorithm. Each lithofacious defined at well will be described by several neural networks. Each neural networks will describe all the lithofacious. And what is the main difference between our classical seismic facies classification and this method? Here we will talk about using several independent neural networks in parallel. So by using several independent neural networks, we will activate different functions, and therefore we will establish different learning rules. Some neural networks will learn from the density of the information. Some will learn from frontier facies, facies between two main clusters. We would like to avoid the impact of the topology, so which is different to the self-organizing mapping approach. We will train the different neural networks with the same labeled dataset. So using a parallel training will provide us with a suite of independent predicted response and prediction to well measurements. So we are establishing different strategies. By using different neural networks with a different activation function, we will solve the resolution issue without an a priori definition of the transfer function between seismic attributes and well facies. Two types of data will be considered. The first is our training data or labeled data. It will be the seismic data, in our case pre-stack angle gathers, and the corresponding lithofacious at the well location. We will introduce what we call an expert information for final tuning of the training set purposes. We call that soft data or unlabeled data. It will be randomly selected after defining the first set of neurons. We have introduced a confidence contribution. Each neural network will vote for individual unlabeled data in a democratic manner. And we use a K-nearest technique to evaluate the response of each neural network. If it reached a threshold, the data will be added to the initial training set. So the contribution of unlabeled data is what we associate to the democratic contribution. We establish a voting system to determine additional soft data. To summarize, this slide is illustrating how the workflow has been established. First, we have the training set, which is the combination between pre-stack angle gathers and lithophases at the wells. We train them through the different neural networks. The user has the possibility to select how many neural networks he wants to select into account. We will define the first neuron set. We will feed the system with unlabeled data. We will go through for each unlabeled data a vote. We will enrich the training set and we will apply for the N neural networks to define the final set of neurons. We use an internal bootstrap validation. From the original data set, we are going to randomly select subsets of data which have the same number than the original set. And we will run the same workflow to validate it. And we can see that as it's a random selection, some subset may have some repetitions. If I take a closer look on this example here, I have an original data set. In this original data set, we have a unique facial recognition. In one of the subsets, we may have some repetitions. So for example, in this case, we have this facius is duplicated. This facius here, the blue one, has been duplicated too. This light orange has been duplicated, and we may see that some of the facias are missing. So we go through the prediction validation using those subsets. And what we will do is, of course, validating the prediction over the leftover. And depending on the result, we validate the workflow. A short summary, for example, and we need to have a look maybe not at each result in particular, but in the global error. And we can see, for example, here, using the bootstrap error, we are minimizing the error over the whole process. And that's where we want to go. Now we can apply for propagating the results, and the decision method that we used is based on a local Gaussian approach to define a local density function. So the facious affectation done by maximum probability or best discrimination rules. An a posteriori probability is computing using Bayes' theorem. So we will compute an a posteriori probabilities of class assignment. So its application now to a specific case study. You may understand by using several neural networks, by using pre-stack data and lithophases, that we can apply this workflow to different geological settings. It could be a conventional, for example, complex channelized environment, or it could be, as in our case, a carbonate reef environment with two different types of deposition, bioerms and biostromes. In some cases, you may not have pre-stack information in your project. So this process you can apply with a selection of different seismic attributes that maybe will characterize the best the elastic properties of your reservoir. The case study, a carbonate reef setting. So we know here this is a carbonate reef, and we have been working mainly on the Permian and Carboniferous reservoir. For the training data, we have used 16 out of the 22 wells that were available. Maybe mainly because some of the wells did not have the full suite of logs were used for generating the lithofacius at the wells. So the input data, seismic, pre-stack seismic data, and angle gathers, time migrated and MO corrected, well lithofacious, rock typing characterization. I will show you how we have characterized the lithofacious at the wells. So we have defined a training set from those data, and it will be our label data. This is the angle stack that we have, and you can see that the top of the Permian is very well marked on the gathers. This is the final interpretation of lithofacious, the different groups that we have determined. Three groups mainly. One is the overall facious outside the reservoir. So we have shell, silicoclastic, both different type of facious. We have the Permian, where we can define some of the most interesting reservoir that we would like to characterize, especially the red one, number 8, where we have the proven oil reservoir. In the Carboniferous, we will have a more closer look, for example, for the facious number 4, which is a good quality of reservoir and oil-proven reservoir. To determine the lithofacious that we have used as the input data, we have been working on 3 axes. One is the lithology, the other porosity, and fluid contents. And this combination will be used as good or not good facious here in our example. So for the lithology, in both reservoirs, we have used the gamma ray and separation neutron gamma ray. We have used for the porosity neutron and sonic, and of course for the fluid contents, the resistivity. And you can see, for example, here that the bioerm and its definition depending on the classification over this reservoir. Carboniferous, exactly the same workflow. We have used lithology, porosity, fluid contents, and the same suite of logs. And we will have here a look for this yellow facious. In this slide, just to show you the correlation between the synthetic and the full stack. We have a good match between synthetics at 2 wells and the seismic data. Learning, predicting. We have 17 facious to characterize over 2 reservoirs. So if we have a look here on the left, we do have the original facious with thin layers. This is coming from one well of our project. Thin layer at the bottom lower part, thin layer, for example, in the upper part here. We have made the decision to remove those thin layers as we want to capture the main good facious. The third track is the predicted facious, and the fourth is a representation of the pre-stack data along this well. At the top right, we have the reconstruction rate after completing the workflow. And we can see that out of the 16 wells, only one is associated with a correlation, a reconstruction rate that is around 80%. All the other 15 wells are more or less associated with a reconstruction rate between 90 and 99%. Maybe for this well, we will need to come back on understanding its location. Maybe it's associated with a fault. Another illustration on how the process is working. If you look on the images here, what we do have, we have first track the original facious. It's taking into account another well in this project. The second track is the predicted facious. You can see very well that in the lower part, the distribution is this vertical distribution has been changed. If we take the third track, this is the upscaled facies. In this case, we took the decision to leave those thinner layer inside to understand if through the process they would be restituted or not. The fourth track is the maximum probability curve. The two next tracks are just horizontal axes, the distribution of facies, so 1 to 17. Vertically, the facies from the whales, and the colors can be associated with the maximum probability. To take two examples, the first green facies here at the top of the whales, we can see that it's the maximum probability, and on the next track, for example, where my cursor is, it's rose. If we go down into our main interval of interest for the yellow facies, the number 4, which is oil-bearing good quality facies reservoir, we can see that we have a doubt between the facies number 4 and the facies number 7. And based on the process with other wells and the maximum probability for some of the reservoir is with the facies number 7. So that's the reason why we have a difference between the original and the predicted facies. So what do we have? What is the result? The result, as it's a probabilistic approach, will be the most probable facies. So the facies with the highest probability. This volume, because this is a seismic volume, can be compared directly, visually, with the wells, as you can see here on this image. So if we take two examples, the good Permian reservoir, this red across this well, for example, is well restituted between the two wells. If we take at the Carboniferous level, for example, here, this good Carboniferous reservoir, the water-bearing, good quality reservoir, and the contact. Another way to illustrate the result is to create a cross-section through those wells. And we can see that, for example, we have a good correlation for the wells on the left here for the good Permian reservoir, and in the lower part for the oil-bearing reservoir. And the oil-water contact is well marked on this volume. The next stage is to understand the distribution of the different facies. So we can detect the geobodies and estimate the volume for each facies as it's illustrated on the right of your slide. How can we now integrate all the results? We know that we have the most probable facies. We know that we will have a probability associated with each facies. Those are volume. This information is calibrated to the wells, so we can directly transfer this information into our geological model and map that onto the geological grid. So here, for example, we have the geological grid, very simple, Carboniferous, Permian, and we have the distribution of good oil biostorm facies for the Carboniferous reservoir. We can eventually run some simulation, and here you see one of the results that we have obtained after running some simulation. So we have the good oil Carboniferous here at this well and its distribution throughout the reservoir. We have the water-bearing probability, which is effectively high, for example, and its distribution you can see here. And we have the shell distribution throughout the reservoir. The worst case and the best case, or the most probable case. So throughout the 100 realization that we did, we were able to determine, for example, the P19 and the P10. So, in conclusion, this workflow is innovative for two main reasons. One, we combine geological information with pre-stack data. So we reconciliate completely the geology and the geophysical information. Second, we use a specific set of neural networks in parallel to learn from the data. So establishing different strategies for learning from the data is one of the key differentiator of this workflow. This workflow is a geologically coherent workflow because we learn from the well and we infer from the seismic attributes, and the result is a facies distribution. It will help us to understand in between wells, which is the most important uncertainty when we talk about facies distribution. Our implementation of this workflow is workflow based. So the user will be able to run scenarios and to establish which one is the best or the most suitable to the data. And of course, it must be seen and understood as a complementary approach to any seismic-driven reservoir characterization workflow, especially when we talk about working in very heterogeneous geological environment, like, for example, generating an acoustic inversion. So it's really a complementary workflow. Thank you.